all right. So again, we're still in chapter 12, okay? Okay, so last time we started looking at distributions, okay? Excuse me, we didn't start. We started looking at normal distributions. That's what I meant to say. Okay, good. All right. And really the most popular one, so to say, is the standard normal distribution. I'm pretty sure I said this last time, but we actually can get a normal distribution for any mean and standard deviation, okay? For any mean and standard deviation. You know, you give me any number for the mean and really any positive number, we can make it a standard deviation and we can get a normal distribution. If I remember last time, I did show how to, no wait, that we'll do today, I'm sorry. I was gonna say last time I showed you how to graph the normal distribution. So through Desmos, you can do that, although I think, anyway, so you can do that through Desmos, okay? And again, I did post the notes and the videos from last time, okay? But really the one that people deal with the most is what they call the standard normal distribution, okay? That's what people deal with the most. And that's where the mean is 0 and the standard deviation is 1. That's the standard normal distribution. I mean, on the, not the next slide, but the third slide, you'll see why the standard normal distribution people deal with the most. Basically, I mean, well, I'll get to that. It has to do with z-scores. Z-scores, a standard score, which is actually also called a z-score. This is how many standard deviations a number is from the mean of the distribution. Okay, that's how far it is. How many standard deviations a data value is from the mean of the distribution. They are actually very useful, as we'll see today, actually. We can actually use them to sort of generalize the empirical rule, okay? To actually calculate the z-score, okay, for any data value x from a normal distribution, you have to use this formula. Namely, x here is the data value. The mean is the mean of that normal distribution. The standard deviation is the standard deviation of the normal distribution. I think I've said before that the normal distribution could be 0, but that's wrong. I apologize for saying that before. So it has to be a positive number. And really from the definition, if z happens to be 0, that corresponds to the mean of the distribution. Really because your 0 standard deviations away from the mean. Z is 0. So if z is 0, you're really at the mean, in other words. If z is positive, then the data is above, greater than the mean. Okay, because if z is positive, then you're a certain number of standard deviations greater than the mean. Negative, though, then the data value is below the mean, okay? Then you're below the mean. That's what happens here. So z-scores do come into play. They are very important. We'll see that today. All right. You can actually express the empirical rule, using standard deviation. If you remember the empirical rule, 68% of all data values are within one standard deviation from the mean for any normal distribution. So for the standard normal distribution, the data, 68% of all z-scores will be within 1 and -1, within one standard deviation from the mean. Again, in terms of z-scores, it's the same as saying between 1 and -1. So 68% of all z-scores will be between -1 and 1. 95% of all z-scores will be between -2 and 2. And 99% of all z-scores will be between -3 and 3. So this is basically the empirical rule, but we're expressing it for the standard normal distribution using z-scores. That's really what we're doing. And if you remember, it is possible, but data values that are further than 3 standard deviations from the mean for a normal distribution, those data values, they're possible, but they're very unlikely. Very unlikely. So with a standard normal distribution, z-scores above or below -3, they're possible, they're just very unlikely. Okay? They're very unlikely. Okay, so that's what happens here. Now, I did try to say, although I might have messed it up last time or the lecture before, why z-scores are so important. Well, this should answer that question. Basically, we can sort of generalize the empirical rule. For instance, we can answer questions involving percentages. So if you have a normal distribution, you can determine what percentage of the data is less than a certain data value, greater than 1, or between 1, or between 2 of them, actually. Like over here, we're able to say 68% of all data values, or z-scores, are between 2 numbers. We can actually generalize that using z-scores, not just to 68%, but to more than that. So we can answer questions, approximately what percentage of all data values are less than something, greater than something, or between 2 numbers. We can do that using z-scores. I mean, you'll see some examples that we do. Okay. So we will do some examples regarding that. Okay. And essentially what we're going to do is we can determine percentages that are less than a data value, or a percentage of data values greater than a number. What we do is we can convert to a z-score and then work with the standard normal distribution. So essentially we can actually convert to the standard normal distribution and play around with that, and then convert back to the normal distribution we were working with. It turns out you can actually use the area under the graph. That turns out to be the percentage. That takes a little bit of work. Why it's true? And it turns out this actually requires calculus, but it turns out the total area under the graph of a normal distribution curve is actually 1. Okay? I mean, I hope this is making sense. When we do some examples, it might make more sense. But before we actually do that, let's actually mess around with z-scores, just for practice. So let's suppose we had a test, okay, that the scores were out of 15, and it turns out they're normally distributed. Okay? They're normally distributed with a mean of 8 and standard deviation 2. So if a student got a 5 on that test, what would the z-score be? What would the z-score for that be? So again, we're going to use this calculation. That's what we're going to use. Basically, we have x is the data value, which is 5 in this case. The mean is 8. Standard deviation is 2. So we have 5. So the z-score, we have 5 minus 8 over 2, which is -3 over 2, which is -1.5. Okay. Notice we should get a negative z-score. And why is that? Because the data value is less than the mean. 5 is less than 8. If this was instead like 9, our z-score would be positive. Or here's another one. What test score would correspond to a standard score of 2.5? So in other words, if we have a z-score of 2.5, z-score, standard score, same thing, of 2.5, what data value would correspond to that? So what data value would give us a z-score of 2.5? So in other words, in terms of the formula, what does x have to be for z to be 2.5? That's really what we're asking here. See? And now it's algebra and we just basically solve it. No, it's basic algebra and we solve it. That's what I meant to say. So messed up the words. So what do? Right? We have this equation. What I did was I interchanged both sides. I like to have the unknown on the left, although really in the long run it doesn't matter. We clear denominators by multiplying both sides by 2, as you can see. So x minus 8 will equal 5, right? So then you just add 8 to both sides, you get x is 13. So the test score, that is a data value here of 13, the z-score for that is 2.5. That's what this is saying. And really, and also again, on this slide, what I was trying to say here, if we wanted to know what percentage of test scores or data values are less than 5 or greater than 5, or between 5 and 13, we can actually determine that, sort of like generalizing the empirical, not the empirical, excuse me, the empirical rule, sort of like generalizing that, and we can use z-scores to pull that off. That's what I was trying to say before. I just didn't know if I was clear or not, so hopefully that made it more clear. All right. Are there any questions on this? I really hope this made sense. We're just basically calculating z-scores if we have a normal distribution and we have certain data values. That's really all it boils down to. We're just using the formula. Because the next one, I figured everyone should try. Okay? Give it a shot. Think about it. So let me stop the recording. Take about 5 minutes. Okay?